Okay, so we'll do problems to practice on fins together. A circumferential fin of rectangular profile is constructed of stainless steel with a conductivity K equals to 43 watt per meter degrees and a thickness of 1 millimeter. The fin is installed on a tube having a diameter of 3 centimeter and the outer radius of the fin is 4 centimeters. The inner tube is maintained at 250 degrees and the assembly is exposed to a convection environment having T infinity equals to 35 degrees and a convective coefficient H equal to 45 watt per meter square degrees. Calculate the heat loss by the fin. Okay, so first, in this problem, we are considering a single fin. Okay, so we have a single fin and we need to determine from the given what is the geometry of the fin. So here they said we have a circumferential fin and they gave us all details. They gave us the conductivity of the material. You can see here the figure of the geometry. Okay, in the geometry, you should, for a circumferential fin, you should give the following properties. So first, you have, as you can see here, this is your fin. It will start at this level, okay? So this is R1. R1 is the radius from which the fin will start. They told us that the inner diameter is 3 centimeters. So the radius is 1.5 centimeter or 0.015 meters. And the outer radius of the fin, which is this one, R2, is equal to, here, look, they said the outer radius is 4 centimeters. Okay, so R2 is equal to 0.04 meters. Now, we know what is the temperatures at the extreme and they said that we have at the inner side a temperature of 250 degrees and the ambient condition are at T infinity 35 degrees. So we have all temperatures and we have the convective coefficient. Everything is known here. We need to determine the heat loss through the fin. Okay, so this is a relatively simple example because we know that for a fin, we have seen together that the formula to get Q is, first, since we have a graph here, from the graph, we can find the efficiency of the fin. So from the graph, we will read the value of efficiency, okay? And we will multiply this efficiency by the maximum possible heat transfer if the temperature of the fin was at T base, which is 250 degrees, okay? So the formula we developed together last time is that if we know the fin efficiency is the actual heat loss over the maximum heat loss if the whole fin is at TB, which is the temperature of the base, which is T0, okay? So over convective coefficient, H, okay, times the frontal area of our fin, okay, times theta base. Let us now determine together what are these parameters, okay? So we can say now then that Q is equal to the fin efficiency to be determined from the graph times the convective coefficient H, it's given, it's 45, okay? Times the frontal area of the fin. What do we mean by the frontal area of the fin? This one, yani the area through which we have the exchange, okay? So whenever you have a circular fin, I will draw it for you here from the top. If you have a top view, okay? This is the area, the frontal area from top, but pay attention, you should consider both the upper and bottom area. So it's 2 times this area, okay? So to calculate this area all you have to do is to consider the area of this annulus. You know that this distance is R1. It's the inner radius of the circumferential fin. And this radius here is R2. So this is the outer radius of my fin. So I can say that the frontal area AF is equal to 2 times, because I need to take the upper and lower frontal area. Both are exposed to the ambient conditions. So 2 times pi okay. Now, please, we should pay attention for something here. If you remember, we said that if we want to use this formula, okay, this graph is developed based on considering a fin with insulated tip, okay? So we said that if we want to consider insulated tip, and it's not the case, here they didn't say that we have an insulated tip, we can correct the length, okay? And instead of R2, if you want, instead of R2, I should replace R2 here by R2 corrected. Okay? And we said, what is R2 corrected? The formula is given here. R2 corrected is R1 plus the corrected length LC. Okay? And we have here, if we consider, if we open, if you want, the fin, it's like if we consider the correction here, okay, you have that the thickness T of the fin is given 1 millimeter. So for the corrected lengths, we should add to R2 the value of T over 2, okay, the thickness over 2. So R2 plus T over 2 will give us the corrected value of R2 corrected. Because if we open the fin, if you want, the idea is the following. You have already a length L, and if you open the tip, you should add from this side, because you have a rectangular cross-sectional area here for your fin if you want, but it's peripheral, okay? And we consider that this thickness is turning over the periphery. So if I open it, I should add T over 2, okay? So my new radius, R2 corrected, is equal to R2 plus T over 2, okay? And we have that R2 is given to be 4 centimeter. We add to it T over 2, which is 0.5 millimeter. So this is R2 corrected, 0.0405. This is R2 corrected, okay? So we have that the frontal area, as we were discussing, is equal to 2 pi times R2 corrected square minus R1 square, because this will give me the annulus area here. So minus R1 square. Okay? So I replace in my formula here, I replace A frontal by 2 times pi R2 corrected square minus R1 square. So this term represents AF. Okay? This is the convective coefficient H. I still have to multiply by theta base. We said that theta base is the temperature at the base, yani at level R1 here. It's given T0, which is 250 degrees, minus T infinity. And T infinity here is 35 degrees. So this term represents theta base. Okay? So until now, this is the maximum possible heat transfer. But you know that actually you don't have the total area at temperature theta base. That's why you should multiply by the efficiency of the fin. So times NF. To get NF, we need to use the graph. Okay? And for this graph, what are the inputs required? as you can see here, at horizontal axis, you need to calculate the following parameter. What is the following parameter? It's L characteristic. And what is L characteristic here? L corrected, sorry. L corrected, okay, is equal to the actual length L. The actual length L is the difference between R2 and R1, okay? So L here is R2 minus R1. And as we said, to correct it, what should we add? We should add T over 2. And here it's given for you. It's L plus T over 2, okay? So this is how I calculate the corrected length LC. And I do LC to the power 3 over 2 times H is the convective coefficient, we know it. K is the conductivity of the fin material. And for AM is defined here in the graph, okay? AM is calculated as T times the corrected length. So we have already found what is LC and we have the thickness, okay? And we can replace and get the value of this parameter. This parameter, as we said, is at the horizontal axis. So at the horizontal axis, we get 0.825. So it's nearly here, nearly. Okay. So we find here what is the location of 0.825. Now we need another parameter. The second parameter is the ratio R2 critical over R1. We have calculated already R2 critical. It's 0.0405 and R1 is 0.015. So we can get the ratio. The ratio R2 critical over R1 is equal to 2.7. Okay, so now all I have to do, if I look at my figure, I don't have the graph of 2.7 exactly, but I can do like an approximation. So if you want, this is the line. This is the line for R2 critical over R1 equal to 2. This is the line of R2 critical over R1 3. I take 2.7, it's closer to curve 3. Okay, so I take, this is from the horizontal axis, I take a vertical line. It will intersect, so this is the two curves between 2 and 3. It's nearly closer to curve 3. Okay, so I can read from this value, I am nearly here. Okay, so it's just before 0.6. So I can read a fin efficiency of 0.59 approximately. Then I am done. Okay, I have everything. I replace the fin efficiency in my formula and I get the value of the heat lost through my fin. Okay.
Doctor, you need to do interpolation to find the exact efficiency?
No need for interpolation. It's graphical reading. Interpolation, you mean graphically, not calculation.
Yes.
Yes. You consider, for example, this is curve 1, this is for 2. If you have 1.5, you take just at the middle between them. If you have 1.7, you take a point closer to 2. But no, you don't have it to take 100% accurate. You have a small error of reading, it's fine.
Okay, thank you.
Yes.
بس ما فهمت كيف جبنا ال R2 critical وال L critical ما فهمت هذا.
Yeah, I will repeat. Look, in the problem, I will show you first the geometry here. Okay, look, I give you this graph, okay? This is, in my problem, I told you have a circumferential fin of rectangular profile, okay? So you can go to this graph, and then in this graph, you say, what are the parameters needed to calculate L corrected? All formulas are provided for you, okay? They tell you what is L, but you can do it also how, because first, what is L? L is the length of the fin, okay? if I give you the radius from which the fin will begin and the outer radius of the fin, what will be the length L? It's the difference between R2 and R1. So the length of your fin is R2 minus R1. Now, what is the concept of L corrected? For L corrected, it's like you open the tip. يعني you have a fin, since you have a rectangular profile, okay? This is the thickness, T, and this is the length L. If you open the tip, it's like if you want, you are extending, you are cutting here and opening the tip. What will be the new length? You have L plus the thickness over 2 from this side. So this is the additional, if you want, lengths to correct, to be able to say that I will use formulas for insulated tip. So this graph is developed for insulated tip. Okay, but actually here you don't have an insulated tip. You can correct the lengths to be able to use this graph. Okay, so you have T over 2 here, and this is L. So what is L corrected? L corrected is the addition of the actual length of your fin plus the thickness of your fin over 2. Okay, and now if you replace L by its value, what is L? It's R2 minus R1. So L corrected is equal to R2 minus R1 plus T over 2. Okay? Also, you can say it's equivalent also to say, what is L corrected? L corrected is R2 corrected minus R1. Okay? And R2 corrected is the outer radius after correction. Yani after correction, what will be the outer radius? It will be the value of R2, okay, plus T over 2. And you can verify this, okay, because when you open your tip, you will have an additional thickness here of T over 2. And the outer radius of your fin will become R2 plus this small corrected value, which is T over 2. So this is equal, if we want to find R2 corrected is equal to R2 plus T over 2. Here they gave it in a second way, but it will give you exactly the same result. They told you that R2 corrected can be calculated as R1 plus corrected length. Yani I take from R1, instead of just adding L, I add the corrected length. And if you replace the corrected length by L plus T over 2, you will get R1 plus L corrected is L. What is L? R2 minus R1 plus T over 2. Okay. So R1 will simplify. And you get that R2 corrected is R2 plus T over 2. Okay. Now, what about AM? AM, that is the parameter that is present here. Okay. You have here to calculate this number, you need AM. AM is given, the formula of AM is given here. It's the thickness, okay, times the corrected length. What is AM? AM represents this area. So if you do a cut here, this area is actually the thickness times the corrected length. We use, instead of just using L, we use LC corrected. Okay, clear?
Yes, doctor, thank you.
Other question? Okay. Let us do another problem. Okay? We have also introduced together last time that we can consider the case of several fins. And if we have several fins, instead of talking about efficiency of one fin, we calculate the overall efficiency. Okay? Let us practice with this problem. The engine cylinder of a moto is constructed of 2046 aluminum alloy. Whenever they give you the type, okay, of the material, I will give you a table, so you can have a table to read what is the properties. And instead of directly giving you the conductivity, I can give you the material, and I will give you a table with it to read the value of conductivity. And is of height 0.15 meter and outside diameter of 50 millimeter. Under typical operating conditions, the outer surface of the cylinder is at a temperature of 500 Kelvin and is exposed. So this is, okay, this is temperature at the base. And is exposed to ambient air at 300 Kelvin. This is T infinity. With a convection coefficient of 50 watt per meter square Kelvin. This is H. Annular fins are integrated with the cylinder to increase heat transfer to the surrounding. Consider 5 such fins. So this is the number of fins we are considering in this problem, which are of thickness 6 millimeter and length 20 millimeters. And they are equally spaced over the cylinder, okay? What is the increase in heat transfer due to the use of the fins? So we want to calculate the increase in heat transfer. We need to compare, if you want, the case with and without fins, okay? First, if we don't have fins, it's really simple, okay? If you consider the case without fins, you just have a cylinder. Okay, a cylinder that is exposed to a temperature. So the whole area of your cylinder then will be at T base, TB. And you have from the outer side, you have T infinity. Okay, so you can say that Q without, if I want to calculate the heat loss, if I don't have fins, it's just equal to the convective coefficient H times the total area of the base. Okay, A base, no, I will put no fins because it will vary. When you put fins, you will have a part covered by fins, okay? Times theta base. So here, all I have to do is to consider the following. I have the value of H, 50. Since it's a cylinder, okay, so I consider the lateral area is this one. So I should do pi d times the height, okay? So it's pi d. You have the outside diameter is given, okay? So pi d times h times theta base, which is TB minus T infinity. This is how I calculate Q without fins, okay? Now, when I put my fins, okay, of course, I expect to have a better heat transfer. And since here I have several fins, we developed together a formula that if we have several fins, we can use the following, okay? We can calculate first an overall efficiency. And once we find the overall efficiency, okay, we say that the overall efficiency represent the actual, the heat loss with fins, heat loss with fins, okay, over what? Over the maximum possible, over H times A total times theta base, okay, where A total represent the total area of exchange. What is the total area of exchange? The total area of exchange will consider the part that is not covered with fins. Okay. So I should calculate this part that is not covered with fins. Okay. Plus the frontal area, the total frontal area of my fins. This is how I calculate A total. Okay. We have two approach here. We can say I calculate I find A total, and to find the overall efficiency, I use this formula. Okay. In this formula that we developed together last time, I need to know the number of fins, which is 5 here. Okay. AF is the frontal area per fin. So for each fin, I find the frontal area. We'll do it for our case here, which is similar to this case, okay? For each fin, what should we do? As we did in the previous problem. For each fin, you have, this is the frontal area. You need to take the upper and lower area of each fin. We take the area 2 times pi, or 2 corrected square minus r1 square, as we did in the previous problem, okay? And NF represents the efficiency per fin. So it's similar to using the graphs that we used in the previous problem, okay? Over A total will represent the total area of exposure, which is N times A fin, plus the area that is not covered from the base. Okay, so this area we added to it. We'll do it in the example. This is a first approach. A second approach, if you want, is to divide the calculation. Is to say that if I have fins, the total loss will be divided into 2 parts. One part that is lost by fins, and one part this is lost by the uncovered area of the base. Lost by uncovered area of the base. Okay? Now, sometimes if you should read all questions before you answer. If they ask you after find the overall efficiency of your system, this means that you should not use this formula before. You should calculate Q total from this formula, and then to calculate the overall efficiency, okay, you do the actual Q total over HA total theta base. So in case after they ask you find the overall efficiency, you cannot use the overall efficiency to find Q with fins. To find the Q with fins, then you divide it into 2 parts. You say, I will find Q total as Q lost by fins plus Q lost by uncovered area of the base. And then once I find it, I can calculate, I replace Q by its value, and I replace HA total theta base to get the overall efficiency. Okay, but if they don't ask after to get the overall efficiency, this means that you can use directly the formula. You use this formula to find N0, the overall efficiency, and once you find the overall efficiency, you multiply it by HA total theta base to get Q total. Any question until here? So now all we have to do is to apply these formulas, okay? But I want you to understand the concept. Even if you don't have these formulas, you can do it. It's really simple. The heat loss is divided into 2 parts. A part from fins and a part from the base area not covered by fins. Let us discuss this in the problem to see it as an example. Okay, if you consider the following problem here. What is the area that is not covered by fins? It is this area, look. This area plus this one, etc. Okay? And to calculate this area, you can simply say the following. You can simply say the area uncovered, area base not covered. Okay. It's what actually? It's the total area of the base equal to area total of base minus area covered. Okay. Minus the area covered by fins. So first, the total area of the base, we already used it here. It's pi d times height. بس هون we should add, yes, this is h. Okay. It's pi d times the height. This is the total area of the base. Now, the area covered, okay? What is the area covered? It's the number of fins times the area covered per fin. And if you look at the following figure, okay? We know the number of fins. We have, as I said, we have 5 fins. We should multiply it by area covered by 1 fin, okay? To find, this will give us the total area covered. What is the area covered by 1 fin? Who can tell me? How you can calculate the area? Yes?
دكتور مش في عنا 3 areas بدنا نعملهم؟
عنا بأي معنى 3 areas؟
عنا الابر 1 انت بكل فن نقول
لا.
عندك السيرفيس
انتبه،
الابر
في
هي ذات
فرونتال، في
اللي من
فرق
تحت.
بين الفرونتال اريا والكفرد اريا. اوكي، شو يعني كفرد اريا؟ يعني انت هلا هيدا السلندر when you put fins on it، اوكي، اذا بتحط one fin here for example, the fin will take a certain space on the cylinder.
thickness.
Thickness 100%. So this is what is called the area covered. To calculate the area covered per fin, you need the thickness of the fin, and you know it. The thickness is 6 millimeter. Okay? So you can say that the area covered is the thickness T times what? Times pi D. Okay? So for each fin, the covered area is thickness times pi times D. If I have n fins, I should multiply by n. And then what will be the area not covered? The area not covered will be pi dh, which is the total lateral area of the cylinder, minus n times pi d times thickness. So I can take pi d into factor. If I take pi d into factor, what do I get? I get, if you want, pi d times the uncovered height, okay? Which is, the uncovered height is the total height minus the number of fins times the thickness of each fin. This will give me the uncovered area, okay? Clear? So the area that is not covered with fins, how I calculate the heat transfer for it? It's just H times the area times delta T, which is theta base. T base minus T infinity. Here I don't multiply by any efficiency. Why? Because this is the temperature. The temperature of the base is TB. Okay? But for the fin, why I multiply by the efficiency? Because actually the temperature of the fin is decreasing. I don't have TB for the whole area. TB is the maximum possible temperature. Okay? So this is why for the fin, to calculate the heat lost by the fin, I use the efficiency times H times A frontal times delta T, theta base. Okay? So first, we determined the area that is not covered. Okay? And we can say now that Q of this area, so Q area not covered, is just equal to H times area not covered okay, times T base minus T infinity. We are done with the part related to the area not covered by fins. Now we move to fins, okay? We have 5 fins and they have all same geometry, okay? So to get the total loss by fins, we should do 5 times or n times. Now, for each fin, how we calculate the loss? As we did in the previous problem. Yani we should find the efficiency of the fin NF and multiply it by H times frontal area of fin AF, okay, times delta T or theta base. Theta base, we have it. Okay, H, we have it. Concerning AF, for AF, it's like the previous problem, exactly same procedure, okay? We say that AF is equal, to be able to use the formula, the graph, I need to find R2 corrected, yani like the previous problem, exactly same procedure. So AF is 2 times, because we take upper and lower part. So 2 times pi, R2 critical square minus R1 square. We have everything. R1 is given, R2 is given. We find R2 corrected, okay? R2 corrected is, as we said previously, R1 plus T over 2. So we are able to calculate AF per fin, okay? And then what is still missing is the efficiency of the fin. And we get it graphically. We get this value graphically like in the previous problem, okay? And once we calculate Q not covered and Q fins, Q total will be the summation of both, okay? This is the first method to calculate Q total. Here in this problem, they didn't ask you after find the overall efficiency. So you can use another method. You can say to find the Q total, I use this formula, okay? I use Q total is equal to the overall efficiency, okay, times H times total area of exchange times theta base, okay? Now, what is the total area of exchange? It's area fins, AF of fins, yani it's AF times N because I have 5 fins, plus what? Plus area not covered, plus area of the base that is not covered. We have already calculated these parameters, okay? So you have area not covered, you have N times AF, you calculate A total. Then you still need to have the overall efficiency. This is the formula for the overall efficiency. And actually, they derived this formula from this analysis. To get what is N0, they said what is Q total, they divided into 2 parts, okay? And then they just took A total into factor to come up with this formula. So now you can apply this formula directly if you want as a second method. So to find the overall efficiency, you have 1 minus number of fins times AF. So this is the frontal area per fin. اللي هي 2 pi